Think about the smartphone in your pocket. It's a marvel of modern technology, compact yet incredibly powerful. It holds more computing power than the room-sized computers of the past, which once filled entire rooms and consumed vast amounts of energy. This revolution is possible because of VLSI, very large-scale integration, a groundbreaking technology that has transformed the landscape of computing. VLSI is the process of creating integrated circuits by combining thousands, even millions of transistors onto a single chip, making devices more powerful and efficient. These chips are tiny, but their impact on our lives is enormous. They are the heart of countless devices we rely on every day. They power everything from smartphones and laptops to cars and spacecraft, enabling advancements in every field imaginable. VLSI fabrication is a marvel of modern engineering, involving sophisticated processes and cutting-edge technology. It is a testament to human ingenuity and our relentless pursuit of technological advancement, pushing the boundaries of what is possible. Imagine shrinking down to the size of an atom. You would see a world of incredible complexity and precision. You could witness the intricate process of building a computer chip, atom by atom, layer by layer, each step meticulously planned and executed. This is the world of VLSI fabrication, where science meets art in the creation of powerful microchips. It's a world where precision is paramount, and even the slightest error can have significant consequences. Even the tiniest imperfection can render a chip useless, underscoring the need for absolute accuracy and control in the fabrication process. The journey of a VLSI chip begins with a surprisingly humble material, sand. Sand contains silica, which is processed to extract pure silicon. Silicon is a semiconductor. This means it can conduct electricity under certain conditions, making it ideal for creating transistors. Transistors are like tiny gates that control the flow of electricity, forming the building blocks of all electronic circuits. The purity of the silicon is crucial. Any impurities can disrupt the delicate process of building transistors. Think of it like baking a cake. If you use spoiled ingredients, the cake won't turn out right. Similarly, impurities in silicon can ruin a chip. The first step in VLSI fabrication is purifying the extracted silicon. This is a crucial step because the performance of the final semiconductor devices heavily depends on the purity of the silicon used. This involves a series of intricate chemical reactions designed to remove even the tiniest impurities. These reactions are carefully controlled to ensure the highest level of purity. The goal is to achieve a level of purity exceeding 99.999999%. This ultra-high purity is essential for the silicon to be used in advanced electronic devices. Once the silicon is purified, it is then melted in preparation for the next step, which is growing a single giant crystal. This process is both fascinating and complex. This process, known as Czochralski growth, involves dipping a seed crystal into the molten silicon and slowly pulling it upwards while rotating it. The rotation helps in maintaining uniformity in the crystal structure. This creates a cylindrical ingot of single crystal silicon, typically several feet long and several inches in diameter. The precision in this process ensures the quality of the crystal. Imagine dipping a lollipop stick into a pot of molten candy. As you pull it up, the candy solidifies around the stick, forming a lollipop. The Czochralski process is similar. The molten silicon solidifies around the seed crystal as it is pulled up, forming a solid single crystal structure. The Czochralski process is not just about forming a crystal, it's about creating a perfect defect-free crystal that can be used in high-performance semiconductor devices. It creates a single continuous crystal structure, which is essential for building reliable transistors. These transistors are the building blocks of all modern electronic devices, making the purity and quality of the silicon crystal absolutely critical. Once the silicon ingot is grown, it is sliced into thin discs called wafers. These wafers are incredibly thin, typically less than a millimeter thick. Each wafer will eventually house hundreds or even thousands of individual chips. Imagine a pizza being sliced into thin, identical pieces. Each slice represents a silicon wafer. These wafers are extremely fragile and require careful handling. Any dust particle or scratch can contaminate the surface and ruin the entire wafer. Therefore, they are manufactured and processed in ultra-clean rooms. These rooms have special air filtration systems to remove even the smallest particles. Section 5. Photolithography, the art of miniature blueprints. Now comes the crucial step of creating the intricate circuitry on the wafer's surface. This is where photolithography comes into play. Photolithography is akin to photography, but on a microscopic scale. It involves using light to transfer a pattern from a photomask to the wafer's surface. This pattern defines the various components of the integrated circuit, such as transistors, capacitors, and interconnecting wires. Think of it like creating a stencil. The photomask acts as the stencil, and light is shone through it. The areas where light passes through will be etched away in later steps, creating the desired pattern on the wafer. Section 6. Etching and doping, shaping the electronic landscape. After the photolithography step, the wafer goes through a series of etching and doping processes. These steps are critical in defining the intricate patterns and functionalities of the semiconductor devices. Etching removes the unwanted material from the exposed areas, leaving behind the desired circuit pattern. This process ensures that only the necessary parts of the wafer remain, forming the foundation of the electronic circuits. Doping involves introducing impurities into specific regions of the silicon wafer. These impurities are carefully selected to modify the electrical characteristics of the silicon. These impurities alter the electrical properties of the silicon, creating regions with different conductivity. This variation in conductivity is essential for the functionality of various semiconductor components. This is crucial for creating transistors, which control the flow of electricity based on their doping profile. Transistors are the building blocks of modern electronic devices, enabling complex computations and signal processing. Imagine using a chisel to carve away unwanted portions of wood, leaving behind the desired shape. This analogy helps to understand the precision required in the etching process. Etching is similar, but it removes material at a microscopic level. The precision and accuracy of this process are paramount to the performance of the final semiconductor device. Doping, on the other hand, is like adding different colored dyes to specific regions of a fabric to create a pattern. This analogy illustrates how doping introduces specific properties to targeted areas, enhancing the overall functionality of the semiconductor. Section 7. Layering complexity, building circuits atom by atom. The process of photolithography, etching and doping is repeated multiple times, layer by layer. Each layer adds new components or connections to the growing circuit. This layering allows for the creation of incredibly complex circuits with billions of transistors stacked on top of each other within a tiny chip. Imagine building a skyscraper floor by floor. Each layer adds new functionality and complexity to the structure. This is one of the most remarkable aspects of VLSI fabrication. It's like building a miniature city, with different layers for transportation, power, communication and more, all interconnected and working in unison. Section 8. Packaging. Protecting the silicon brain. Once all the layers are formed, the wafer is diced into individual chips. Each chip is then tested rigorously to ensure it meets the required specifications. The functional chips are then mounted in packages. These packages provide mechanical support, protect the delicate chip from damage, and provide electrical connections to the outside world. Think of the chip as a brain and the package as its skull. The package is like the interface between the chip and the rest of the device. It provides the necessary connections for power input and output, allowing the chip to communicate and interact with the outside world. Section 9. VLSI, the invisible engine of modern life. VLSI technology is the invisible engine that powers our modern world. It enables the creation of smaller, faster and more powerful electronic devices. From smartphones and laptops to cars and spacecraft, VLSI chips are ubiquitous, enhancing our lives in countless ways. The continuous advancements in VLSI fabrication drive the progress of various fields, including healthcare, communication, entertainment, and artificial intelligence. As VLSI technology continues to evolve, we can expect even more innovative and life-changing applications in the future. It is a testament to human ingenuity and our relentless pursuit of technological advancement.